Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
So, this equation, the force, the magnetic force, is equal to E times V cross B. That's saying that the force, which is a vector, it has a magnitude. That's what that little arrow above the F means. It has a direction and a magnitude. Okay? 50 newtons north, 60 newtons south. Okay? And that's equal to the charge here. Now, in some equations, you'll see that expressed as Q. It just means the charge of the particle you're talking about. In this case, with a particle accelerator, we're talking about proton or an electron. Either one, whether it's positive for a proton or negative for an electron, is going to be negative. So you have E. And then you have the velocity of that proton. Again, you got that little arrow above it. It's a vector. It has a magnitude and a direction, okay? 8.0 times percent of the speed of light in the horizontal direction. It has a magnitude and a direction, okay? All right. Now, this is trigonometry, sines, cosines. We'll talk more about this later, but again, it's mathematics trying to express that three-dimensional relationship between the direction of the proton in the particle accelerator and the magnetic forces that it is experiencing by virtue of it going through the quadrupole magnet, okay? Mathematical tool, okay? Mathematical tool. So far we have analytic geometry with my drawing. We have calculus with the power series. And now we have, and don't forget, analytic geometry is a combination of algebra and geometry. And now we have trigonometry, okay? All right. Oh, we're clicking, aren't we? All right. So, because the angle of interaction between the proton's trajectory and the magnetic field, the force, is 90 degrees, the sine of 90 degrees is 1. And this is trigonometry. So you go from the force cross with the magnetic field, the charge times the velocity cross with the magnetic field, simplifies to the magnetic force is equal to EVB, where E is the charge of the proton, V is its velocity, and B is the magnetic field. And you notice all the little arrows above went away because now we're talking about magnitude in that quadrupole magnet down that Z axis. All right. Let's do a little bit more, shall we? Yes, let's. All right, so force, mass times acceleration is equal to the negative of the charge and the velocity. And remember, the magnetic field is all vertical now. So that's why instead of saying B, we can say BY. Now, here's where algebra comes in. I know I said analytic geometry had algebra and geometry. Well, now here's algebra straight up. You have this equation. Mass times acceleration is equal to the negative of the charge of the proton times its velocity times the vertical component of the magnetic field. Now, here's the algebra. You take this term, and remember the negative means it's a restoring force. The force, the magnetic field, is trying to push the proton back towards the z-axis. It's a restoring force. It's trying to bring it back in. So that's where the negative comes from. And I know I talked about how you got to put the real in the equation, the physics in the math. All right, so that's why the negative's there. So here's the algebra. You take the negative EVBY and you bring it over to the other side, and it becomes positive. So you have mass times acceleration plus the charge of the proton times its velocity times the vertical strength of the magnetic field. And that's equal to 0 because you brought this term over. Okay, that's algebra. I think we'll stop here for now. I think that's a good bit of mathematics, right? And when you see this next term, oh, we're back to calculus. You see how you have mass times acceleration? Mass times acceleration? Well, you have mass, but this d squared x with respect to t squared, that's the calculus representative of acceleration. It's the second derivative of distance with respect to time. More calculus. I told you we were going to have a lot of math, didn't I? All right. So let's continue next week, shall we? All right. We're getting a full menu of mathematics. Analytic geometry, calculus, algebra. Okay? And there's a lot yet more to come. Just remember all of these tools, the analytic geometry, which is algebra and geometry, the power series, which is calculus, the algebra that we use to manipulate the equations so that we can understand them. They're tools of physics, okay? All right. So tune in next week. Same fat time, same fat channel. Okie dokie. And remember, fat physics with attitude is demonstrated by Oscar Balundini. Enjoying physics as the window into our amazing world of nature and mathematics as the tool to open that window. So let's continue on next week. Okie dokie. So, as we have seen, the diagram that represented the position of the proton in the X and Y plane with respect to the Z-axis, that's analytic geometry. That is a combination of algebra and geometry. And you could definitely see the geometry. The algebra comes from using the coordinates of the object on the X, the Y, the Z axis, using those coordinates. Now, we first encountered analytic geometry with that diagram. And then we went on to the power series, which is from calculus. And the power series was just to get a handle on the dependency of the magnetic field of the quadrupole, the X and Y components of that magnetic field on the vertical and the horizontal components of the proton's position. And we saw how it made sense, right? With the power series for the X component, we saw that when Y is equal to 0, the horizontal component of the magnetic field is 0. Makes sense. And we saw that when the horizontal displacement is 0, then the vertical component of the magnetic field is 0. So once again, an equation is only a value if it correctly describes what we see, whether it's with our senses or by experimentation, which would be by our senses too, right? So that makes sense. We've seen that the horizontal part of a quadrupole's magnetic field depends upon the vertical displacement of the proton. And we've seen how the vertical part of a quadrupole's magnetic field depends upon the horizontal displacement of the proton. And that physically agrees with those two power series for the horizontal component of the magnetic field and for the vertical component of the magnetic field. So you see how the two have to be in agreement. We observe a physical phenomena, and then we try to come up with equations to help us understand that physical phenomena. So far in my project, we've had analytic geometry and calculus and algebra. Because don't forget, for algebra, we did that little switcheroo, and you know I wanted to use that word, when we were saying force is equal to mass times acceleration, which is the magnetic force of the quadrupole magnet on the proton, right? So we equated mass times acceleration to the magnetic force, which wound up to be the charge of the proton times its velocity times the magnetic field, okay? And that cross action with the sign, that was trigonometry, okay? So analytic geometry, calculus, trigonometry, and algebra. All right, and there's a few more to go, believe me. All right, so I'd say that's about enough for now, wouldn't you? That's a good serving of mathematics. All right, so please tune in next week, and we will continue on because there's other areas of mathematics we have to get to before we can come up with those equations of motion. We got differential equations to go through. We got partial differential equations to go through. We have matrix methods to go through. And we have boundary value problems to go through, okay? So we're going to have fun. Okie dokie. Tune in next week. Same fat time, same fat channel.